And hello, welcome back to this video of boundary layers. So today we're going to go through von Karman solution. So last few videos I've been talking about ways in which to solve the boundary layer equation via similarity solution. That is by some very tedious manipulations so that you will get, you'll get the solutions that you need. So today we're gonna talk about the other kind of solution. It's called integral solution. It's somewhat more intuitive than, let's say, a similarity solution, which can get pretty abstract at times. But let's see, but it's sort of more approximate. Okay, it's more approximate, and it's a little bit more, how shall I say, more approximate. It's an approximate method. Let me get my blackboard out. Okay, so this is the, I should not be using that. Here we go. So what's the idea behind von Karman solution? Okay, von Karman solution is pretty simple to understand. Okay, so, and it's not only applicable to flat plate flow, it can apply to more general kinds of boundary layer flow, but in this video we're going to do flat plate as usual. Alright, so picture yourself again, you have your free stream coming in, okay, at u infinity. Okay, so and then a boundary layer will start to develop as you go along. And okay, let's say you are at a distance L into the, you're a distance L into the system. Okay, and you want to have a gauge of what the wall shear stress is. Okay, of course you can use a similarity solution to do this. I think as of this video I have not posted how the similarity solution should look for tau, but I can probably do a comparison later as to what the final answers actually are. But I just before doing that, I just want to go through the methodology. Methodology is pretty important, so I'll go through that first. Okay, so this is what we have here. We want to estimate tau, which is the wall shear stress, because friction factors are pretty interesting to us. We want to find ways of developing them. Okay, so what can we do? Okay, so von Karman had this idea. Okay, let's consider this control volume. Okay, let's consider this control volume right over here, and this is going to be shaped like a trapezium. Okay, trapezium. Trying to write my best with the mouse here. Hope that is neat enough. So this is going to be a trapezium, and how do you want to find your wall shear stress here? Okay, so what do? You can consider a force balance. Force balance. Alright, force balance. So you have the top of the trapezium. Okay, you have the bottom of the trapezium, the left, and the right. And now, what force are we interested in? We are interested in the wall shear stress in the x direction. So naturally, we'll want to do a force balance over the x direction. Okay, so that's what the idea of integral analysis is about. We are not doing a differential. Okay, we are not going through. We're not going to look at a differential volume, dx, dy, dz. Differential volume. This method is more of the Navier-Stokes, pure Navier-Stokes. Over here, we are like starting our force balance from scratch, which is the same idea of evaluating forces across a control volume, except this control volume is much bigger, and of course it's we evaluate across this length here, delta x. okay, instead of dx dy dz. This is just along a axis, an axis dx. Okay, it's just yeah, dx is it's just along the x direction. Along the y direction and along the z direction, of course, dz you don't really care too much about because it's 2D, right? But along the y direction, you're not doing the differentiation, so to speak. So you're only doing the discretization, or you're actually taking limits along the x-axis, not the y-axis. So that's one of the reasons why you can say this is a what do you call that? A solution which is approximate. Okay, it's an approximate solution. So that's von Karman for you. So without further ado, let's start the force balance. Okay, so we are interested in tau x, which is wall shear stress for x direction. And what then do we need to do? We perform force balance on the boundary layer in x direction. Okay, so that's the idea of what we are doing here. So how are we going to do that? We look at the diagram and see the trapezium. Okay, so let's use the graphics. Okay, I have a graphics template, LaTeX graphics, and let's do uncomment. Alright, so this one's important. So let me save a picture of this, and then or rather export a picture of this, and then use that. Okay, so this will be here in here, heat transfer. Oops, sorry, heat transfer, convection. Now I'll just save it here. Von Karman BL. Okay, so this should be a PNG file. And just export. Yeah. So that I want to von Karman boundary layer. Alright. Hopefully this works well. Yeah. Alright, so now we see this. Okay. That's given us a little bit better. Okay, of course along a blackboard, not a whiteboard. So remember, let's take a look at some of the forces. Okay, so sigma or sum of forces equals to, okay, force along the x direction equals to the top plus bottom plus left plus right. So contributions from the top, bottom, left and right. Okay, of course there may be an accumulation of force within here, but we assume a steady state, right? So there will be a accumulation term, which we will just assume is 0. Okay, there will be an accumulation term because you can actually accumulate forces within this control volume. Okay, so for example, if you keep applying forces within this boundary, this control volume, yeah, you can accumulate the force in the x direction, but that must be sort of balanced, I guess, by some dissipation term as well. Long story short, things can happen inside this control volume, and that's accounted for by the accumulation term. But the accumulation term is 0 for a steady state solution. So accumulation. Okay, so we'll start this from the outset. Accumulation term equals to 0 within the control volume. So accumulation of momentum. Okay, so this is all like, you know, forces, you know, rate of change of momentum. So yeah, that's summation of forces. Now of course, if this thing isn't going left or right or anywhere, the summation of forces should be 0 in equilibrium. In equilibrium, okay, sum fx equals to 0. Of course, fy equals to 0 as well, but we don't really care about fy at this moment. So let's consider the force terms one by one. So let's take a look at the bottom. The bottom will have a force per unit area of tau x. Okay, and what's the area? The area can be some y length. I mean z length. Sorry, because you have length along the z direction. So I just call that LZ, and I'll times the x length. The length of the x direction is delta x. Alright, delta x. Okay, so that would be equal to the bottom contributions to the force in the x direction. Okay, so LZ is some length in the x direction. Of course, later on you'll find out that everything just cancels out very nicely, so no problem. Now let's consider the left part. The left part, we will have, what forces do we have here? Okay, now let me make a correction first before I continue. Yeah, in equilibrium, the sum of forces is 0. However, this should be balanced by, okay, it's not exactly 0 because I forgot to kind of mention that there's actually fluid flowing in and out. So I would say, let's put it this way, rate of change of momentum, rate of change of momentum in control volume. Okay, so let's do that. Rate of change of momentum in control volume. Okay, so yes, anyway, let's continue where we left off. So yeah, that's something I forgot to kind of introduce. So accumulation term, yeah, that is just 0. We don't assume a rate of change, time varying force, because this is a steady state problem. Now let's take a look at the left. The left has some pressure, so it's the pressure on the left. Okay, it's the fluid static pressure, or just the fluid pressure itself. It's not just a static pressure, it's all the pressures, you know, sort of combined together, outside the dynamic pressure. Of course, you don't have stagnation, so you don't put dynamic pressure there. So okay, what's the thickness over here? The area here is the y thickness, so to speak, and that is delta. And of course you have LZ as well, and all of this must be evaluated at x. Okay, and let's do the same thing for the right. It's basically the same thing, except you have, okay, x plus delta x. Now again, I want to make something very clear. Momentum boundary layer thickness is, I use delta p. Okay, this small delta p will be the y momentum boundary layer thickness, and this should be right. Okay, this should not be left, it should be right. Now the more challenging thing, of course, is how do you then deal with the top? Okay, how do you then deal with the top? Okay, so as said before, we assume the top is some kind of trapezium. So I'm going to delete this picture, so it's not useful for us anymore. The top I assume is some sort of trapezium. So let's do a trapezium, and let's take a look. Okay, so this is actually delta, and this is delta at x plus delta x. All right, so this delta at x. Yeah. Yeah, draw the x properly. Okay, so let's see. What's the contribution to force on the system in the x direction? It will be, well, there's an area here. Okay, so force equals to, okay, pressure on this plate. There'll be some pressure that's on this plate. Pressure, okay, because you can talk about it like an integral of pressure dot dA, right? Pressure dot dA. And of course, if you want to be so strict, pressure, then you sort of have this you sort of have this theta here, so you can write dA cosine theta. Okay, so it's this cosine theta is over here. Do you want to do it that complicated? I mean, yeah, this dA, right? Yeah, you don't want to do it that complicated. It's not necessary. But the approximation, okay, we use an approximation. Okay, we use an approximation. Okay, so the dA cosine theta, we still use this area, or A cosine theta, which is this normal area here, if I'm not wrong. The normal area here. Okay, this is A cosine theta. What is it? It is, okay, again, we'll need to sort of have this length over here. There's this length over here. And what is this length? Okay, this is the boundary layer at x plus delta x. Okay, so this is the length, because it's the difference between these two lengths here, minus the boundary layer thickness at x. Okay, and of course that will have to multiply into the z direction as well, which we just call it Lz, and we just find that we cancel all of that out later. And what is this pressure then? We use some sort of average pressure, P average. Okay, we have a P pressure average. And how do we average the pressure? It's a very cheapskate kind of a method. So we say that the pressure at the average of the average pressure is the pressure at x plus pressure at x plus delta x, and just take an average of them, like literally. So this is basically how we get the forces acting through the top. So the top was the part where we just did a very kind of a approximation method. Okay, so let's continue. Okay, P, okay, the top one equals to, just write down this expression, P at x plus P at evaluated x plus delta x, and you divide the whole thing by 2, and delta at x plus delta x plus, I need the big delta there, and you'll see why we are doing this x plus delta x thing. We are just going, later on we are going to reduce delta x to 0, okay, and then we see what happens when we take the limit delta x equals to 0. But before that, we will just do it the normal way. Okay, so there's a pre-average here, and then we have to minus delta and x. Alright, so now we have sort of evaluated the force terms. Then we'll need to consider the other terms that go through like the boundary layer. I mean, we have to find the rate of change of momentum in this control volume by considering the inflows and the outflows of fluid. And that will be, of course, in the next video. Okay, so thanks for watching. I'll see you again. Bye-bye.